The theme of today's lecture is Rabi oscillation, and this is also the last theme of this chapter on the two-level quantum mechanics. And so the purpose of this first chapter was to basically rewrite quantum mechanics. So I wasn't trying to say anything new or anything that you're not already familiar with, but mostly try to recast them in the formalism that's usually not taken in the undergraduate curriculum, mainly using the bra and ket notations, and also emphasize more of the sophisticated linear algebra techniques like projectors, and the unitary transformations, and so on. So this more advanced level of linear algebra really helps in theoretically navigating the ways of quantum information sciences, which is why I felt important to talk about them at the beginning of this course, and I hope I've done that. Okay, so after finishing up these quantum chapter with a discussion on the Rabi oscillation, then and from the next video I'm gonna start talking about the well, guess what? Next chapter will be on the entanglement and how to characterize the degree of entanglement through the mathematics of singular value decomposition, also known as the Schmidt decomposition. And along the way, I will also introduce the idea of entanglement entropy, and hopefully discuss some examples of entangled state. Okay, so and the reason why I call them chapters is because I am preparing kind of a manuscript for this course, which I will upload as soon as the semester begins. So then there will be in the style of a book with chapters covering different themes. And the first chapter will be on the discussion of two-level quantum mechanics. Okay, so now let's get down to business. So the Rabi problem is the problem of the spin dynamics when the magnetic field is given by this form. Okay. So in terms of a picture, there is a static magnetic field with the size B0 coming out of this page. In addition, there is this rotating magnetic field. Okay, so there's the rotating magnetic field whose magnitude is B1, and it's rotating in plane with the angular frequency equal to omega. Okay, so actually this problem is fairly complicated. in the sense that there are three energy scales in the problem. Okay, so there's the energy scale of B0, which is a Zeeman energy. And there's the second energy scale, which is the in plane, maybe I should say in plane, well, Zeeman. Since the magnetic field both has out of plane component and the in plane component, I need to associate an energy scale for both of these magnetic fields. Okay, and furthermore, there's a third energy scale coming from multiplying the angular frequency of rotation of the in-plane magnetic field by h bar to turn it into some sort of energy scale. Okay, so when the problem contains several different energy scales, we know for sure that the problem is rather intricate and harder to solve, but hopefully, due to the complexity of the problem, something interesting comes out from the analysis. And of course, this turns out to be a very interesting problem, and that's the whole reason why we are studying it carefully. Okay, so with this choice of the magnetic field, my Hamiltonian, which is sigma dot b, with the full time dependence on, is like this. B0, B1 minus omega t, B1 plus I omega t, and minus B0. So we have both the diagonal elements and the off diagonal elements, which are also time dependent. And due to the explicit time dependence of the Hamiltonian, it's not possible to say that the solution of the Schrödinger equation is simply that. It's not going to work out anymore. And normally this sort of a time-dependent Hamiltonian is not possible to solve exactly unless you get really lucky. And one does get really lucky with the Rabi problem. So what Rabi must have thought when he when he sat down and tried to solve this problem was that this field is rotating, and that's the source of this entire headache. But he also probably recalled from his the old courses he took as a student that if the observer also rotates with the same angular frequency, then of course this rotation will not look like a rotation, rather it will look like a static magnetic field. Okay, so if one can solve the problem in rotating coordinates, then that will be great. And since it's obvious that in this stationary coordinate, it looks quite hard to solve the problem. It's worth a shot and try to solve the problem in the rotating coordinates. Okay, so in the classical mechanics, one goes to the rotating system by making this sort of substitutions. Um, Sorry, I think this is V. Yeah. So there's this change in the definition of the velocity because now the velocity appears to be different to an observer who is rotating with this angular velocity vector. And there must be a similar way to implement the rotating coordinate frame. And to figure out how to implement the rotating coordinates, one has to recall the fact that the solution from the Zeeman problem actually offered a clue. Okay, so the Zeeman problem said that if you have a static magnetic field, then you have some sort of let's say the Zeeman field was directed along the z-axis, so this phase factor was proportional to sigma 3, and this operator acted on the initial state. However, if the initial state happened to be lying in the xy plane, then the result of these time evolution is the rotation of the magnetization within the xy plane with the angular frequency of omega. Okay, so that was precisely the solution that we got in the previous video, talking about the solution to the Zeeman problem. And one can also view that solution as a way to kind of go from the frame where the spin is held stationary to the frame where the spin is rotating at this angular frequency. Okay, so that was the rough idea that Rabi must have had. Okay, so how did he actually implement it? The way he implemented it is by writing the state vector as a product of two different things. So the first term that he wrote was E of I omega t sigma 3 over 2 multiplying some other state vector. Okay, so I'm not gonna bother to justify the use of this particular phase factor. You will see why by directly working with this new representation of the quantum state. So let me go ahead and apply the temporal derivative on this new representation of the state. Now, because there are two different functions that the derivative can work on, you're going to end up with two different terms. So you can take out this overall factor. And then this time derivative can either act on this new wave function, or it can act on this phase factor and bring down a factor of minus 1/2 omega times sigma 3 acting on psi t. Okay, now this must be equal to the Hamiltonian acting on the on the wave function. So we have this equal to ht acting on I omega t sigma 3 over 2 and psi t. Okay, so now let me move this factor to the left. Okay, and then rewrite the Schrodinger equation in this form. So now the Schrodinger equation is in terms of this new wave function psi, not the old one. Okay. So then, if anything, I seem to have made this. I seem to have made this worse, right? I mean, if I move this piece, I can move this to the right-hand side, and in fact, write the whole thing as. Let me erase some parts. Okay, and move this expression slightly to the right. Good. So now what do I have? Plus. Okay, and I'm also going to get rid of this. Okay, so that's the new Hamiltonian. And let me call this H prime T. If anything, this new Hamiltonian H prime looks much more complicated than the old one. Remember this is old Hamiltonian we had, and I mean with a minus sign, of course. And this is the new Hamiltonian we have, H prime. And I mean, I have to let out a sigh because obviously this looks way more complicated than what we started out with. But here a kind of miracle happens. Okay, I mean that's the whole reason why we are doing this exercise of transforming to the so-called rotating basis. So what happens is nothing short of a miracle. In fact, instead of getting more complicated, it gets a lot simpler. So the new Hamiltonian is minus B0 minus omega B1 omega minus B0 acting on the new wave function. Okay? Well, if you are in doubt, then you should really check this out yourself, that this expression inside the red box really reduces to this expression without any time dependence whatsoever. Okay, so what happens is that there were these time-dependent unitary transformations. Okay, and these time-dependent things, they kind of came in and struck out these phase factors which were time-dependent, and then the new Hamiltonian became time-independent. because the time-dependent phase factors that were here and here, they got erased by these unitary transformations. Okay, so once we have these sort of a time-independent two-level Hamiltonian, we know how to do everything exactly. Okay, so this is exactly solvable now. Good. So the idea is to write the original state uh, in terms of some phase factor multiplied by another state. And then this state becomes now exactly solvable. So therefore, the original state is also exactly solvable. Okay. Well, to make things even simpler, I'm going to pretend that I can tune. It's not pretending, it's something you can actually realize easily in a laboratory. So there's nothing pretentious about it. Uh, I'm going to tune. Yeah, tune is a much better word. I'm going to tune omega to coincide with the B0. In other words, the energy associated with the frequency of rotation, h bar omega, is equal to the Zeeman energy. Okay. That can be done, right? Because you can estimate you can figure out the Zeeman energy of a particular spin by other means, and then you can translate that into some frequency. So that beforehand, you know what sort of frequency range is required to make this happen. So it can be, a couple of gigahertz or maybe terahertz, or depending on the spin that you're trying to manipulate. Okay. Once this tuning occurs, then this Hamiltonian becomes even simpler, since we have both diagonal elements equal to 0 now. And we just have to solve this a simple off-diagonal matrix problem. And the solution to this is immediately obvious. This is in fact solved by writing B1T sigma 1. Yeah. Acting on some initial state. So we have an exact expression for the time-dependent quantum state of this problem, which is this phase factor multiplied by this second phase factor acting on some initial state. That's it. That's the exact solution. Yeah, that's the exact solution. Okay, so now once we have such an exact solution at our disposal, we can calculate whatever we want. Okay, so what do we want to calculate, for example? let's say we can calculate, for example, the average expectation value of the spin. Let's say expectation value of sigma 3. Okay, but in order to do so, we must have some knowledge of the initial condition. And for the initial condition, we choose to be the plus z state. Okay, so here's the thing. I have an external magnetic field B0 along the z-axis, and I have my initial spin state also pointed along the same axis. Okay, so in an ordinary Zeeman problem, this is already an eigenstate of the Zeeman Hamiltonian, which means that such an initial state will not change its status over time. It will remain stationary. However, when there is an additional rotating magnetic field, which is called B1, and the important thing is that B1 is time dependent, then what could happen, what must happen, is that this spin, which was initially along the Zeeman axis, namely along the z-axis, now flips, and then flips back, and then flips back. So basically, it executes a rotation over time. And how do I know that it executes a rotation? Because if I calculate this, then one can find the following result. Okay, that's it. So as a function of time, t, initially the sigma 3 average was +1 because it was fully polarized along the direction of the Zeeman field. However, over time, it oscillates back and forth. And you can predict at what time exactly this complete reversal of spin will take place, because that will happen at exactly half the period, and that and the half the period is exactly 1 over b1 times pi over 2. Okay, so if you plug in that time in here, then you will have cosine of pi, which is -1. So the statement is that we will know exactly when the spin flips. And that's a very powerful statement, because you cannot really see the spin. Spin is just an atomic phenomenon, and so there's no way you can control. You can contact individual spin and try to flip its direction, but by solving this problem, you can have a very big confidence that if you arrange your apparatus in this way, with a certain kind of a static magnet in one direction and another kind of a oscillating magnet in the orthogonal direction, you can be you can be actually very certain that the spins will execute this rotation and flip its direction at the expected period. Okay, and this sort of control over the spin is a powerful gift that one can have in order to have a coherent control over the spin dynamics. And such kind of control, of course, plays a vital role in coming up with some sort of a quantum computer. Okay,